Howdy, this video is on solids. Solids compose a large fraction of compounds in the world. Some of the interactions that hold solids together are unique to solids. Hopefully, after watching this video, you should be able to describe what a unit cell is, describe the characteristics of a cubic unit cell, describe the different types of solids and the forces that keep them together, and put a series of solids in order of increasing melting point based on the interactions that hold them together. So for solids, the particles are close together. This intermolecular forces are much more important than the kinetic energy. There's always motion at the atomic level. For solids, typically that motion is just vibration. Solids tend to be highly rigid and incompressible. Crystal structures consist of stacked unit cells. And so the blue is our unit cell, and if it gets propagated in all three dimensions, we can recreate the crystal. You can kind of think about a crystal as being analogous to a molecule. If you take a molecule in a liquid and you propagate it in all directions, eventually you get the solution. You do the same thing with the unit cell. Unit cells are the smallest repeating unit that has all the symmetry characteristics of the crystal.
In solid cesium chloride, each cesium ion, here colored blue, is surrounded by 8 chloride ions, and vice versa. The crystal structure is constructed from its unit cell by stacking the cells together without any gaps in between.
It's kind of cool. There's only 14 possible types of unit cells. And so the top 3 are cubic unit cells. And so you have the primitive cubic, where each of these circles correspond to either an atom, an ion, or a molecule. And so for this is called simple cubic, you have a particle on each corner. This is body center cubic. You have a particle in each corner, then one in the center. And then face center cubic, you have particles on each of the corner, and then each of the faces. But again, each circle can be an atom, an ion, or a molecule. And so for the cubic unit cells, the edges all have exactly the same length, and the angles are always 90 degrees. You have tetragonal unit cells, where notice that now we have 2 different lengths. We have A and C. And then you have orthorhombic, where you actually have 3 different lengths, A, B, and C. So each edge is a different length. And then you also have monoclinic, where now you no longer have 90-degree angles. Triclinic, hexagonal, and trigonal. But we're going to be mostly concerned just with cubic unit cells. And so again, simple cubic unit cells, particle in each corner, body center cubic unit cell, particle in each corner plus in the middle, and then face center cubic unit cell, each corner and each face. And so cubic close packing of frozen argon, and if you notice, you have particles each corner and each face, and so that would be face center cubic. And you can also have for methane. Now again, each circle, remember, can correspond to an atom, ion, or molecule. And so for argon, the circle corresponds to an atom of argon. For methane, it corresponds to a molecule.
Shows how the 3 cubic unit cells arise. Arrange a layer of spheres in horizontal and vertical rows. Note the large diamond-shaped space among the particles. Placing the next layer directly over the first gives a structure based on the simple cubic unit cell. Those larger spaces mean an inefficient use of space. In fact, only 52% of the available volume is actually occupied by spheres. Because of this inefficiency, the simple cubic unit cell is seen rarely in nature. A more efficient stacking occurs if we place the second layer over the spaces formed by the first layer, and the third layer over the spaces formed by the second. That simple change leads to 68% of the available volume occupied by the spheres and a structure based on the body-centered cubic unit cell. Many metals, including all the alkali metals, adopt this arrangement. For the most efficient stacking, shift every other row in the first layer so the large diamond-shaped spaces become smaller triangular spaces, and place the second layer over them. Then the third layer goes over the holes visible through the first and second layers. In this arrangement, called cubic closest packing, spheres occupy 74% of the volume. Note that it is based on the face-centered cubic unit cell.
And so we have these 3 cubic unit cells. And for the simple cubic, only about 52% of the volume is actually occupied. It's a very inefficient way of packing. For the body-centered cubic, it's 68. For the face-centered cubic, it's actually 74. And so that's the most efficient way of packing. Now, if you think about it, the more efficient the packing, the closer the particles should be, and the stronger the intermolecular forces should be. Also, we can think about in terms of particles per unit cell. And for the simple cubic, you have a particle in each corner. And so each particle on the corner contributes an eighth to the unit cell. And so you have 8 particles, each contributing an eighth. And so that gives you 1 particle per unit cell. For the body-centered cubic, again, you have 1 in each corner. That gives you 1. And then 1 in the center. And so that would give you 2 particles per unit cell. For the face-centered cubic, you got the corners, which again contribute 1. And then each particle in the face, half of it is in this unit cell, half of it's in another unit cell. And so 6 faces times a half gives you 3. 3 plus 1 gives you 4 particles per unit cell. The coordination number is just the number of next nearest neighbors. And so for the simple cubic, if you think about this particle here, then you have 1, 2, 3 nearest neighbors. Now there's going to be 1 opposite up here, there, and there, and so that gives you a coordination number of 6. For the body-centered cubic, if you think about the one in the center, it's surrounded by 8, and so that gives you a coordination number of 8. And then for the face-centered cubic, this one's probably the most difficult one to see. If we take this particle here, and we think about, okay, so we have a corner particle, and we have these faces. And so there's going to be a plane here, and this particle will be next to its neighbor with 4 faces. Now, if you think about another plane, you'd have another 4 faces, and then the third plane, another 4 faces. 3 times 4 gives you a coordination number of 12. Again, coordination number just corresponds to the next nearest neighbors. Now, again, simple cubic, not very efficient, not very common. And so polonium is the only known element that uses simple cubic. A body-centered cubic, you can have iron, sodium, potassium. I think all the alkali metals. And then face-centered cubics, aluminum, copper, silver, and gold. And so there's different types of solids. And again, they base on how the particles are held together. So for metallic solids, you have what's referred to as metallic bonding. Ionic solids, you have the ion-ion interaction. Network solids, you have extended covalent bonds. And the molecular solids, you're just going to have dipole-dipole interaction or London dispersion. Now, of these 4, molecular solids tend to have the lowest melting points. There's a lot of overlap between the top 3, and so it's hard to say which one's going to have the highest melting point. And I also should mention that sometimes a solid will have more than one type of interaction that holds it together. So like for glasses, you have covalent bonds, which makes it seem like a network solid, but you also tend to have ions to keep everything charged neutral. So for metals, you have positive ions in a sea of conduction electrons, and that actually leads to its properties. And so because you have ions in a sea of conduction electrons, metals tend to be malleable, ductile, good electrical conductivity because electrons can move, good heat conductivity because again the electrons can move, wide range of hardness and melting points. But again, it's kind of cool if you think about a metal. So the metal atom lost an electron, that electron goes into the conduction band, and then you're left with these positive ions in a sea of conduction electrons. And again, it's the mobility of the conduction electrons that accounts for its luster, its malleability, ductility, electrical and thermal conductivity. And so the way of thinking about why it has a luster, light comes in, causes electrons to move, vibrate, and that actually causes light to go out. It's malleable because if you pound on the metal, you actually don't break the bond. You just move the ions, and the ions will still be surrounded by conduction electrons. It's also kind of cool. If you want to tweak the properties of metal, you can actually form an alloy. And so an alloy is just a mixture of two or more metals. And so, stainless steel is actually a mixture of iron, carbon, chromium, and nickel. It resists corrosion. Plumber solder, you need a low melting point, and so it's going to be lead and tin. Sterling silver, silver and copper. Gold is too soft to be used in jewelry, so often gold is mixed with another metal to make it a little bit harder. For ionic solids, you just have positive ions and negative ions, and so you have the ion-ion interaction, which causes them to tend to be rigid, fairly high melting points, poor electrical conductivity, and often water soluble. And the properties actually come from what's holding the particles together. Now, the thing about the structure of ionic solids is it's often built by taking a cubic lattice of ions of one type and then placing ions of an opposite charge in the holes. And which structure it actually takes depends on the ratio of the radii. And so if the ratio of radii is less than 0.4, the structure tends to be zinc blende. If the radius ratio is between 0.4 and 0.7, then often you'll get a rock salt structure. If the ratio of the radii is greater than 0.7, you'll often get a cesium chloride structure.
Many elements, covalent compounds, and, as you'll see in the next two examples, ionic compounds adopt cubic closest packing. Sodium chloride adopts the sodium chloride or rock salt structure, as do many other alkali, halides, alkaline earth oxides and sulfides, and other ionic compounds. Picture separate face-centered cubic arrays of chloride ions and sodium ions as they approach and interpenetrate each other. The smaller sodium ions fit in the holes between the larger chloride ions and the NaCl unit cell. Zinc sulfide adopts the zinc blende structure, as do the copper-1 halides and several other compounds. If face-centered cubic arrays of zinc ions and sulfide ions approach and interpenetrate slightly offset from each other, each ion becomes surrounded tetrahedrally by 4 of the other ions. Note the blinking zinc ion and the 4 sulfides. You can see the relative positions in this slightly expanded view of the zinc blende unit cell.
And so again, it's kind of cool. Thinking about it, you got the face center cubic, and then in this case, you got the sulfur in these holes. Now for the sodium chloride, the chloride ions were also face center cubic, but the sodium were in these holes. And so the different holes because the ratio of the radii were different.
Sodium chloride can be built by first constructing a face-centered unit cell of chloride ions. The smaller sodium ions can then fit into the spaces or holes between chloride ions. Notice that each sodium ion in one of the lattice holes is surrounded by 6 chloride ions at the corners of an octahedron. Therefore, the sodium ions are said to fill octahedral holes. The relative sizes of the ions of cesium chloride make it possible for the cesium ion to fit snugly into the hole between 4 chloride ions. In contrast, sodium ions are relatively small. The distance between the sodium and chloride ions is too great for the sodium ions to be attracted to the chloride ions when occupying that hole.
And so you want the particles as close as possible. The closer, the stronger the attraction. Stronger attraction, lower energy, the more stable.
The structure of sodium chloride is, therefore, different than that of cesium chloride.
And again, you just think about it in terms of a different ratio of the radii. Now, for ionic solids, the absolute charge of the particles is the most important in determining the relative strength of the ion-ion interaction. The larger the absolute charge, stronger attraction, larger lattice enthalpy, higher melting point. Secondary consideration is the smaller ions, closer ions, stronger electrostatic attraction, larger lattice enthalpy, higher melting point. But again, the size of the charge is the most important consideration. For network solids, atoms are held by covalent bonds in 1, 2, or 3-dimensional networks. Now this will give you a wide range of hardnesses and melting points, typically not soluble in water. And so you can think about diamond. Each carbon is covalently bound to 4 other carbons. It produces a 3-dimensional structure. Graphite, each carbon is covalently bound to 3 other carbon atoms. Now this one's a little bit different because you're producing a plane. So you're producing a 2-dimensional structure for the covalent bonds. And then the 2 layers are attracted to each other with London dispersion forces. And so remember, sometimes solids will have more than one type of interaction. So for graphite, you'd say it's a network solid in 2 dimensions, and then actually London dispersion in a third. Here we have diamond again. Silicon has the same structure as diamond, and you can actually form silicon carbide by replacing some of the silicon in the carbon, for the carbon.
Diamond, an allotrope of carbon, and silicon have the same solid structure. Chemists take advantage of this similarity by making silicon carbide, which combines some of the hardness of diamond with a much lower cost of production.
And then finally, molecular solids. The molecules will just be held together by London dispersion, dipole-dipole, or hydrogen bonding. And so because of this, molecular solids tend to have the lowest melting points, poor electrical conductivity. And so C60, discovered about 40 years ago, it's a molecule composed of 60 carbon atoms. Now remember, on those unit cell pictures we had the little dots, and so in this case the C60 would correspond to one of the little dots. The little dots can be an atom, an ion, or a molecule. And so C60s are face-centered cubic lattices.
The spherical C60 molecule is attracted by induced dipole intermolecular forces to other C60 molecules. The C60 molecules pack together as efficiently as possible, which means that each C60 molecule is surrounded by 6 others in a layer. As successive layers are added, the result is a face-centered cubic arrangement of C60 molecules, with each molecule surrounded by 12 others.
And so it's held together just by London dispersion forces. And so that's fairly weak, and so you'd imagine that the melting point should be relatively low. Ice obviously is held together with hydrogen bonds.
Ice is held together as a solid by hydrogen bonds. When ice melts to liquid water, the regular, relatively open structure of ice collapses. Liquid water can be more efficiently packed and denser than ice.
And the structure for ice is relatively open to maximize the hydrogen bonds. And that's why for water, the solid is actually less dense than the liquid, which is fairly unique. And so as you heat the ice, you're adding kinetic energy to the molecules. They start moving a bit, and then eventually they'll be able to partially overcome the intermolecular forces. But it's kind of cool. By understanding the forces that keep the particles together, we can actually understand the properties of the different types of solids. So metallic, you have positive ions and C conduction electrons, which leads to it being malleable, ductile, having luster. Ionic, you have the ion-ion interaction, which leads to a fairly high melting point. Network solid, you have extended covalent bonds, which leads often to being pretty hard, like in terms of graphite. Molecular solids, they're held together by dipole-dipole, dipole-induced, dipole, or London dispersion, or hydrogen bonds, and so they tend to have the lowest melting points. I hope that was helpful.